That's only Zoom, apparently. All right. Okay, thanks everybody for coming and for listening to me talk about galaxy morphology. And so I'll talk about the low surface brightness universe this time around. And I'll hopefully explain what low surface brightness means in this context. The definition changes a little bit over time, but effectively it is below the brightness of a typical night sky. So if you're at a nice dark site, you can only go to a certain brightness, and then at some point you just see the night sky. So it depends a little bit on what wavelength you're observing at, what location you're observing at, how good your integration in instruments are. So low surface brightness is a little bit of a moving gatepost. But we have been trying to learn how to do low surface brightness, and I think we've actually come up with a good definition now. And so uh, we started with Hubble's classification scheme. You'll see this slide, or you see this particular um, classification between ellipticals and disks, galaxies, and disk galaxies with bars. You see that pop up all the time. So that's our that's where we hang our hat. And so we start with bright, nice galaxy pictures, but is that all there is? And so if you start looking at these Hubble pictures, you start to notice that, yeah, the eye is drawn to the center, and then you've got these spiral arms, and then it sort of gets a little fuzzy, and there's still little blue dots there, and then is that a foreground star? Is that still part of it? And so it becomes a little less clear what's part of the galaxy and what isn't. And so galaxies are fuzzy. Disk galaxies, especially, sort of have no clear edge there. And so defining where the edge lies is already hard. And then also, how far does that go? And even if you look at them edge on, you see that same effect, right? It just keeps going. The further away we get from the disk, that's like, yeah, it's fainter and fainter and fainter, but it doesn't seem to have a hard edge anywhere. And so if we model our galaxies, you often end up with, subtract all that light that you model pretty well, and then there's something left over. Often in the center, there is something like a bar feature or something like that that pops out. But also you see that there's a little bit left uh, further out from the disk. At some point, you go like, I'm not sure if I'm convincing myself. There's a fantastic Hubble quote. We always find ourselves at the edge of our detectors, so peering into the noise, hoping to get a signal that's barely any more than the noise of the instrument that we're looking at. I'm not doing it justice. I should look it up. And so we start understanding what all of those components are. And so we start defining these profiles. And actually, these profiles describe the disk or the whole galaxy pretty well. But it does kind of beg the question to how far out, because you see that the postage stamp is neatly cropped and the line only goes to a certain point. So where exactly does the galaxy stop? And so first we start with the vertical profile. So the vertical profile, as we look at the edge-on galaxy, in fact, this edge-on galaxy, Pete van der Kruijt in 1981 came up with a profile description for edge-on galaxy disks to say like, okay, this is how you can model the whole edge-on view of a galaxy without that dark stripe. So typically from ground-based data, the brown stripe wasn't as clearly visible. And so there is this central surface brightness and then a radial dependence and then this K, which is a truncated gamma function, which is really an exponential on its side, like integrated exponential disk, and then with a secants hyperbolicus, like sec h squared vertical dependence. So you can kind of go like, wow, how did he come up with like a function that complicated? Well, this is back in the day when people didn't do a lot with computers, and so there was a there were sort of shortcuts. If you have an exponential, but you have to put it on its edge, like, oh, that actually integrates as this gamma function. So that was the mathematical description for the disks, and that seemed to be working really, really well. Um, and so we can characterize how thick these disks are and how far out they go. And so we have those, but either way, we look at it edge on, we look at it face on, they seem to keep going, all right? So we can model the exponential disk, and that's that red line here. And so as the disk continues, you kind of go like, does this never stop? Is there just lower and lower surface brightness, just fewer and fewer stars? At some point, it becomes probably moot because you have like 1 star per kiloparsec or more, and so you wouldn't be able to pick that up either. But it does feel like, does it go to infinity? Because these models are sort of set to extrapolate to infinity. Because we typically run into the night sky or the zodiacal light, so the light that gets reflected by dust in our own solar system, or some sort of background, some sort of like all sky effect. So the better the image, the longer the integration, always something interesting, something a little, the galaxies grow a little bit. So you can actually, if you look at a picture longer, or the galaxy longer and longer, you see the galaxy grow in size some. So first thing that popped up is the fact that some disks seem to truncate and some don't. And so type, and unfortunately, astronomers being the way they are, they find three things and they call it type one, two, three. I'm sorry. I wish that these were a little more descriptive. So you have type one, no break. It just keeps going. The isophotal profile just keeps going. It's a straight line, as you can see, right? The red line there. Then there's a point where you can have a truncation, a bend, a downward bend of the profile. So you do have an exponential disk that stops, then transitions to another exponential disk that actually has a faster, like goes down faster. This was originally found as sort of the point where the disk wouldn't grow even if you saturated it more or you exposed it longer because there was no light to grow it noticeably. So initially, this was called truncation. The disk stops, but as longer exposure images, even longer exposure images became available, they noticed that, oh no, it started growing again, just at a slower rate. And so it's not quite truncation, it is a sort of downward bend, but the disk does seem to stop there for a minute. And then there's also the inverse that's true. So you have an exponential disk, you fit an exponential disk, and then it actually seems to have a little extra light. So it has a flatter disk, exponential disk. So it seems to have like two disks in the type 2 and type 3. So you have a down bend, you have an up bend, and you have the no break. And so it was kind of interesting to see, like, okay, do all disk galaxies fall in these three? I mean, they sort of have to, but like how many in each category, for example. And so as we are getting now all sky surveys that are deep enough, we can start getting the numbers for how many downbend, how many upbend. Upbends are the least likely ones. I think it's about 10%. But type 2 seems to be very common. So something like 50-50 between type 2 and 1 and type 2. Um, so do galaxies have no edge? There's no, I mean, it gets fuzzier and fuzzier, and you simply run into the sky noise, but also other galaxies. So there's already another object. So it's like you can't tell. And so it's very hard to fit or say what the typical size is. And but we did actually try here. So either you have that light profile, you have like an effective radius that gives you a scale. It doesn't give you the edge of the galaxy, but it gives you like a typical size of it as it's, if I go from a central point to halfway of that central point, this is my half-light radius. So that's like I have these effective radii. If I use a Cersei profile or the Vauquelin profile, there is a typical scale involved. But as you can see here, if you've got an E's plus, so that's like a group or cluster central galaxy, like these massive ellipticals. And then we have an SBC, which is sort of a typical Milky Way size disk galaxies. Then we have these tiny ultra diffuse galaxies or dwarf galaxies. And so the effective radii of all of those are very different. But you'll notice that there's also a little R1, and R1 is a way to define the edge. And so quite like this approach where instead of saying, oh, it's going to be this light or it's going to be this filter or it's going to have to be a particular um, uh, threshold. The threshold here is not observationally defined, but as a like, okay, when do we get to one solar mass per parsec squared? So that is a surface density. So if you can understand what the stellar population is, you can figure out what the actual edge, that R1 edge is. So let's seem a little physically motivated. Um, there's others. So there's R25, which is the surface brightness. So that's just the edge of the galaxy as it looks in the Vauquelin catalog. So that's based on a photographic plate. We defined the elliptical around it and said, okay, that's R25. And so the Vauquelin basically produced those in the RC3, which is the original all sky galaxy catalog. And so that's the one that we've used for ages. So you'll see R25 pop up, but it is completely motivated by how far you could actually see in this particular survey with a particular filter and everything. The Petrosian radius is a way to is sort of in between everything, which is like, okay, well, if the outer isophode is 20% of the enclosed area, then that's the Petrosian radius. Honestly, effective radius, Petrosian radius, both of those are sort of we've got the whole profile and we're trying to infer like a more general pattern. And then the R1 from Chamba and collaborators, she has defined that R1 as the one solar mass per parsec squared. And that seems to be something that you can then translate into various filters. So that's the purple line you see here. And it seems to be a better way to sort of enclose most of the galaxy rather than that dotted line, which is the effective radius. It's a decent scale, but that depends very much on the whole profile. And so the purple line is like, yeah, as soon as you get to a certain mass density, that's where we're calling it. But as you can see for all these pictures, there's little fuzz still sticking around, right? There's still not all of these galaxies are completely contained by their purple line, but that purple line is sort of our okay, that's the galaxy and everything outside it. That's the low surface brightness features. It's a little bit of a arbitrary almost line, but that if I talk about the galaxy as a whole, I think the purple line is a pretty good one. And then the outer features are outside of it. So why are we so interested in why go to this low surface brightness is because like anything outside the galaxy, you can sort of imagine the bigger scale we get, the longer it takes for any kind of orbit to completely complete it. So for instance, on our own Milky Way, we rotate around the center of the galaxy every, I think it's a half gig a year. So it's like 500 million years. So that's sort of a typical scale for mixing time. So all the stars and stuff get mixed within that time. So if you're interested in something that you want to see if it's longer, preserved longer as a grouping of stars, you go further out because it takes much longer for the whole orbit to complete. And so it's a fossil record of the past galaxies that came in. And this is called galaxy archaeology because essentially we're dusting off little remnants of what the whole galaxy originally was made of. And so the ages, the fractions of star in that stellar halo, all the predictions of galaxy formation models. Effectively, if I smash a whole bunch of galaxies together right early on, then I should see some of the bits still flying around in the halo. If I essentially only do one galaxy every billion years or so, I should see a completely different stellar halo. So these are sort of broad predictions of the galaxy formation models. So there's two ways to get to low surface brightness. You can either well, you have to be pretty stubborn to do it one way or another. So you want to take a deep picture. You want to take a very deep picture and you kind of go, well, I've got my iPhone. We got really sensitive cameras now. Like that's absolutely true, but you still have to integrate for very long times. So you're trying to beat the night sky. So you have to subtract something that's brighter off the faint stuff that you're trying to see. So you have to beat down the noise, which means that you just have to integrate for a really, really, really long time. The exposure times for a typical picture is typically in days. So several nights of observing need to be combined in order to see one galaxy. Or you can say, like, I'm going to grab a couple of stars. I'm going to grab a couple of these I'm going to see like if I can resolve the individual stars in these fainter structures. And because they're not so bright, right, the stars are pretty separated out. So I can actually identify individual stars and then count up how much light there is from each individual point. That helps, that works only if you can resolve the stars. So really, this is only something that you can do with nearby galaxies. And then often you have to go to Hubble or something, a space-based camera. But that's a different way to do it. Counting stars you can do with the ground from around Andromeda, because Andromeda is the nearest other galaxy. So that's the first time this was done, and you can sort of see the little squares as the camera had just patiently went through every, you can sort of see it in the left corner as well. That was the first run. That was just around. So that's basically the red area now. And then deeper and deeper with, further tiling further out and further out. So as you can see is that, and then you count the density of stars, and suddenly you realize that, yeah, this doesn't keep going as neat elliptical areas. Suddenly you see streams, you see blobs, you see empty bits. Start seeing lots of little dwarf companions. There is sort of a bridge between M33 at the bottom and Andromeda. So there's like a bridge of stars going from one to the next. So you see suddenly a lot of features. You see at number 5, for example, is a plume coming out of the halo. There's like this stream at 4. 3 is I think, a disrupted dwarf. So there's all these kind of like, oh, lots of stuff has happened. But because it takes a really long time to complete an orbit, you still got basically the leftovers from when that happened billions of years ago, because that stream hasn't made 5 orbits and sort of diffused into the halo. How common is this? So if you look for papers by either primary author Martinez Delgado or he's a co-author, there's loads of these beautiful pictures of galaxies and then this faint stuff around. This is the best example where I find amateur I have to put into quotation marks, because honestly, this is no longer amateur stuff. The amateur stuff feels like, well, I'm doing this on a weekend for fun. I don't care about the quality. I'm doing this for my own enjoyment. This is high quality work, right? This is so it is unpaid astronomer, I would say, but people who have their own pretty good setup to do a telescope and a pretty good camera, and then just pick a galaxy and just stare at it. Very, very long integration times, then carefully stacked on top of each other in order to see those faint streams. And so you see these loops where a small galaxy was torn apart and looped around the galaxy. You see these plumes where it basically went straight through, and then that is sort of the where the kinetic energy of the whole of the galaxy sort of stops, and so you get a plume of the point where the all the kinetic energy has been transferred into potential energy, and then it all falls back, so you get shells around galaxies. So you notice that basically every galaxy that they look at has some features around it, and no two of them are alike. They're very similar looking things, but all of them seem to have something original happening to them. X like X orbits, a weird plume with a gap in it, something's going on. And so there's lots of structure. And so to the left there, you see the Needle Galaxy, especially edge on. You can catch a lot of these plumes and streams and what have you. And so what we're seeing is lots of galaxies have faint structures around them, but in order to understand them, we should start thinking in the terms of like, well, what happens if a small dwarf galaxy falls into the halo of a bigger galaxy and then basically gets disrupted? And so the bit of the galaxy that fell in first accelerates first. So first the galaxy elongates and then eventually spaghettifies around the main galaxy. And so modeling these things is quite interesting. And so as you can see here on the left, you've got the Sombrero Galaxy. So typically you get like the Sombrero Galaxy, beautiful stripe in the middle. That's now all shrunken down to a much smaller area. And you can see very faint that there's sort of a loop around it. And that loop was then modeled to see like how old is it? What kind of velocities can I see? Can I see from the stars with spectroscopy and the Doppler shift how much movement there is? So that's the thing that we're after, like see and understand these faint streams. And so how many satellites do I need for one of those interactions? And often you end up like, well, I just needed one Magellanic cloud-sized thing, but it is now smeared over a very long area, a very long stream, and therefore over a very large area. So now the whole thing is low surface brightness. And as you can see at the bottom, these are models, these are n-body models of to reproduce the particular morphological effects that we're seeing in these low surface brightness features. And it's getting pretty close. Like we understand this pretty well. There is, however, one thing that can sort of spoil our fun here, and that is, as you can see the streams here, it's always dust. If anything messes with astronomers, it's if it's not coordinate systems and magnitudes, it's dust. And so this is dust in our own Milky Way, and it's at high latitude. So it's up high from the disk in our galaxy. It's been sort of ejected, and so it has all these swirly, wonderful shapes. But as you observe these galaxies in great depth, you start picking up the reflected light from these swirls of dust. So we're basically seeing dust reflection. But because and you go like, that can't be a lot. It's like, no, but the deeper you go, you start picking up every faint signal, and one of them is galactic cirrus. So you get it. I still think this is a fantastic sight. These are really pretty shaped clouds and what have you, but it's not the low surface brightness features that we're hoping to see. Galactic cirrus is pretty much everywhere, and so at some point you run into this as a limiting factor as well. Now, these things, I'm going to go technical on you for a minute. This is really hard to do because you need to subtract the sky first in order to see what's underneath it. So it's basically, if you have a count rate of the background, the sky is 100, you're trying to see a little feature that's 10. So how do I subtract 100 off the image correctly? And often you end up with first, you have to sort of, as you see all the circles here, that's like blocking off any star, anything that's actually a source, and then trying to determine what if there's any gradient in the light, because often you end up with like, well, one side is a little brighter than the other, so you actually get a gradient, not a flat value. And so once you subtract that, model that correctly, then you can subtract it. This is very hard and actually even difficult to do, and especially automate. So this is very much the part of the astronomy where experience matters, and knowing how to do that is almost is more of an art form than it is than it's fully technical. So as soon as you do that, that's great. But then you have another thing, and as you can see in all the wonderful James Webb pictures, but also others, all stars basically are not perfect point sources. They always end up with like this diffraction spikes, and also around them just a very dim halo. And you kind of go, well, how bright can it be? Because look, if you have a really bright star, that halo can outshine that faint stuff around a galaxy that you're trying to see. So you start with an original, you have the galaxy there, you model every bright star in the field, often ones that are, arc minutes, if not degrees away, and you subtract the light, you subtract the contributions. So you can subtract the scattered light, and then what you're then left with, if there's still fuzz left around your galaxy, you believe that a lot better. So this is something that you cannot get away from. All telescopes have scattered light. All telescopes will not reproduce a star as a point source. So there will be light scattered about. And so this is something that you're just going to have to live with if you want to do it this way. If you want to get low surface brightness features around a galaxy, you're going to have to live with the fact that you have to do sky subtraction, or at least background subtraction, and the fact that nearby stars will scatter light. So go deeper and deeper and deeper. And as you can see, like, so top left is Sloan. Sloan Stripe 82 is sort of like an extra deep version of Sloan. And then with the Canadian French Hawaiian telescope, honest to God, that's what it's called because it's built by Canada and France and on Hawaii. So it was a sort of consortium. But that's a very good deep imaging telescope. So it goes down to 29th magnitude per arc second. So it goes even deeper. And then with Granticam, which is on the Canary Islands, they went even deeper still. So you can see, like in a Sloan, you see a couple of small galaxies. And then in Sloan 82, you see a few more. And then you go to CFHT, like all of the ones that's like a little fuzzy thing in Sloan suddenly has grown already to a much bigger source. And then as you keep going, like, oh wait, there's like fuzz around this galaxy as well. But you need to really drill down in order to get there. So larger and larger telescopes, set more and more sensitive cameras, and then also very careful background subtraction and scattered light subtraction. There's even entered the Dragonfly. So I love the fact that, first we did one thing, which was just bigger telescope, bigger camera, stare at it longer. And at some point, a couple of astronomers realized that the sports cameras, and especially the telephoto lenses that they use for stadium pictures, were so good they could actually they are compatible with a good astronomical mirror. So we went back to using lenses in astronomy for like 100 years. All our telescopes have mirrors, but this is an array of telephoto lenses, and so they diffract the light, they don't reflect the light, and so there is less of the issue with the diffraction spikes. There is less of an issue with PSFs. There's still a PSF, but it's much more contained. Um, and you just add all the lights from all the different telephoto lenses together, and you end up with the pictures on the right. So that turned out to be very, very good. And while not cheap, a lot cheaper than a very large telescope. So this thing is completely optimized for low surface brightness pictures, and so has been taking low surface brightness pictures, except for that M31 here at the bottom. That's still that star count that we saw earlier. So in the outer disks, we start seeing things like this, where we have like, okay, there's a little bit of a bump thanks to a spiral arm, then we have a loop, an outer loop, and then we get an edge. And then as you keep going, like, oh, I can model this better and better, but we still need to be below 30 magnitudes per arc seconds to start seeing the swirls that have been predicted by galaxy models. But you start seeing these things pop up with Dragonfly. So there are some controversies, and I'm going to go over them. There's on the one hand, we have in the Galaxy M101 that I started the lecture with. It says like, yeah, there is fuzz, but there isn't as much fuzz. There isn't a stellar halo around this galaxy. Our Milky Way, Andromeda, every galaxy that we've been able to look at has some like diffuse light around it, but M101, no such thing. And then the other one was we see one loop in this Edge-on so Martinez Delgado's in 2008 found two loops, and the Dragonfly study found one loop, not two on the left in that little pink box. So the issue is like, what is happening in that second loop? Is that even there? So, and then the last one was also ultra diffuse galaxies. So this is a almost completely new field. We did talk about low surface brightness galaxies before, but ultra diffuse are even fainter and also don't have defined spiral arms. They just seem to be tiny little fuzzes of stars. We did see these things in original telescope observations, but often they were sort of mistaken for blemishes on the telescope or blemishes in the detector. But these ultra diffuse galaxies, you can sort of see them with Hubble. They look like this. So these are the Hubble pictures. You can sort of see that it's a little lighter in the center. That's it. That's the whole galaxy. So it is really faint and hard to pinpoint where the center is or how many stars there are. So it's also very hard to get follow-up observations because you then have to go figure out how do I get a redshift for that or how do I get a spectrum? Because it's this little fuzzy blob. I could be off and not know, and it would take a very long time to get a spectrum of that. So with star counts, you can then, for instance, follow these up and actually see if you can resolve various things. So M101, that halo, we can find the red giant branch stars. So if we do it in two colors, we get the MS is main sequence, which is, do I have a cursor? No. So if you look at the plot in the bottom left, there's MS, there's AGB, and there's RGB. MS is main sequence, so those are sort of the main stars that haven't evolved out. RGB is red giant branch, and AGB is asymptotic giant branch. So the RGB and AGBs are giants, so ones that have evolved off the main sequence. So you can look for RGB stars. They live typically quite long. So we can find the RGB stars, count how many there are, correct for any missing stars, and then convert the whole thing into a light profile. And so you can see how that compares and do that in every Hubble field that you can get on this thing. See how many main sequence, how many AGB, RGB stars there are. So the main sequence is the blue, the AGB is the orange, and the RGB is the pink, and it's on the top right. So the legend's in the top right, the red box. So you count those, you see how many of those there are, and then you see what that profile looks like, because that's a profile that you couldn't pick up with even the dragonfly. So you can see how many there are and compare it directly to the profile of the dragonfly. So they line up well. We're all in agreement. And I find this is a good example of scientific rigor and scientific method. One, we have somebody makes a claim. They have a very accurate, very nice paper on like showing like, hey, here's the profile. This is what it looks like. And then we use a completely different technique to verify what they saw was in fact correct. So hopefully that convinces you because yes, there is absolute almost no stellar halo. That red green line is sort of where like that's where you expect the stellar halo to contribute. So there is a little bit. If I look at just the disk, that's the dashed blue line. So it's not just the disk, but there is only very little extra as far as the amount of additional light. So how much halo there is. And so M101's halo. So that galaxy does have, in fact, an anemic, an underperforming halo. So halos and models how many stars are in that stellar halo in the fuzzy diffuse part, and the M101 is all the way at the bottom there. Does that compare to what we see in other galaxies? They all typically have uh, a couple of percent up to like 10% of the stars are in fact in this surrounding halo of stars. And so the model predictions are the color boxes. And so for a particular mass galaxy, you expect them to be there. And M101 is almost breaking that rule. So that's interesting. But we can also look back at disk truncations with stellar counts, for example. So we can go in and say like, hey, in AGB stars, those are the old stars versus young stars, the main sequence stars. And then we have some intermediate stuff like, and so we can look at those and see if that break that, the profile truncated, that type 2 break, if that's the same in each population. And the answer is no. So the young stars are much harder truncated, and then the older stars, that has a much fainter truncation. And that's probably because stuff gets scattered out of the one disk into the outer disk. And so you expect the stars that live longer for that to be a easier transition than the young stars, which basically all got formed in the main disk, and only a few got scattered out to the outer disk. So you can do the same thing with warps. A warp is sort of like if you've got an edge-on galaxy, there's sort of like there's sort of a little loop that, it's warped. It's got like an S-shaped. You can see this here with so it's down bending on the left side and a little up bending on the right side of the galaxy. We see that in gas, but do we always see that in stars as well? And so the old stars do not show that that warp, but the young stars seem to follow the gas. So maybe some of those young stars were formed in that gas. So the gas drives this warp. And we've been trying to figure out how galaxies get warped because like there are these neat disks, and then suddenly there's a little, but it's on both sides. So how does that happen? Is there some precession happening? Is this something like gas flowing in, not quite on the edges, but a little bit like this? So that last one seems to be the case, at least here. So we can find dwarfs also this way with stellar population. So we suspect there's something there, but then we look at it with Hubble and then count the stars and then say, okay, how many stars do I see in each like little block, or can I draw like a line around it? And that's what you see in the top, in the bottom there. I quite like this because like it's a good way to get morphology, to actually get a shape out of this thing. Um, you can also look for, star formation. Hey, and in these faint outer regions, do we see any star formation happening? And so this is another way to do that. So you do these really deep integrations, but look only in H alpha emission, so one emission line. And so back in 2001 and actually a little bit before that, Annette Ferguson did that in a couple of galaxies, and we find these also in ultraviolet. So we get these extended ultraviolet disks. So there's star formation, there's stars, gas, and all kinds of stuff still happening far, far, far out of galaxies. Oh, this is something that you can also then do, combine them and say like, hey, if I see the gas, do I see the UV? And they seem to be following each other around. This is something that I'm interested in. Um, okay, I'm going to have to step out for a second. Sorry about that. Sorry about that. You playing? Okay. So the outer disk, so you see the blue contours here, that's the gas. And then in black and white is the ultraviolet. And so ultraviolet light seems to be in some of the contours and sometimes not. But one of the issues with ultraviolet is that or the nice things is that there's not a lot of background light. You have to go to space. So all these are space-based observations because ultraviolet light doesn't come through our atmosphere. So you have to go to space, and there isn't a lot of scatter, there isn't a lot of background light. So you have nice dark background. This is great. I can actually see low surface brightness effects. That's true, but then you get little blobs, and you don't know if it belongs to this galaxy or not. And so you can see um, these contours in gas, and then you can say like, oh, but if I see it sort of contoured around a gas blob. Sorry, the gas contours around this little black and white dot that I see. That has to still belong to the galaxy as a whole because the gas belongs to the galaxy as a whole. It's not a background galaxy or is a background source of any kind. So you see the little red lights, the little red dots everywhere. So this is where the authors went through and found dots around what they thought was like the outermost dot for these outermost star-forming region for this galaxy. Because it's interesting to see which galaxies have star formation happening in the very outskirts on the shores of these island universes, as if you want to get poetic. And it's interesting because we think that sort of shows where gas is flowing into it, got dense enough and actually forms stars before it reaches the rest of the galaxy, rather than some galaxies that don't have that. And at the bottom DDO 50, you can sort of see like it all plumes out at one end. That's probably because it's going through a halo of hot, like it's going through a cloud of hot gas that's sort of stripping away the gas of this galaxy. Something's funny downstairs. All right. So the low surface brightness. We're within a year of Rubin Observatory starting observations. That picture there shows that the entire telescope building is done. At the bottom, you see this is the camera baffle. This is where the camera is going to go. It's already on there now, I think. It is the biggest digital camera ever made. It is a huge camera, as in it is the size of a person at the shutter. So it has a you can literally stand inside this digital camera. It has so many pixels that if you print it out at the normal resolution, you'd actually print something out the size of a football field. So high resolution, uh, really big camera. Why do we do this? Why did we do this other than say that we've made the biggest camera ever? Is to take a picture of the whole sky but with a really large telescope, so you're sensitive to like faint things. So look for things that go blip, supernova, variable stars, asteroids that are moving, like anything that's moving or twinkling or something like that. Go look for those. That's the main reason, but because it's taking a big picture all the time and it has a lot of light collecting area, it's going to be, if you combine all the images, you're going to get something really, really deep. So we're going to see all this stuff that I talked about for the whole southern hemisphere. So galactic cirrus, streams around galaxies, bridges, all this stuff, it's going to pop out for every galaxy you can think of, not just staring at one galaxy, it's going to stare at all of them. So the low surface brightness universe holds a bunch of clues for the origin of galaxies, like because we did has every galaxy eaten smaller galaxies? How many have they absorbed? But because of the long time scales involved means that we have a little bit of a record. So that's like that first infall is still happening. It's maybe looped around once, possibly twice, so we can actually see that stream of stars. It's very technically challenging. Even we're now been preparing for Rubin for a while now, and it's going to still be very interesting if we can do this everywhere. Subtract the sky, okay, get the PSF, the point spread function, how the telescope behaves really with bright stars, get that under control. So we have dedicated telescopes, and we can try to do that with star counts, where we use Hubble. But the fun thing is now we'll have Rubin Observatory. That's good for those long integrations. So that is not with resolved stellar populations. But then we also have two space telescopes that have the quality of imaging of Hubble, but much, much larger fields of view. So suddenly we don't have to take like each individual picture and then count the stars in there. We'll have a picture of the whole galaxy and count stars, in ellipses around it. Like there will be plenty of opportunities there. So both Euclid and Roman. Euclid is the European Space Agency mission. It has already been up for almost a year now, and eventually it will take a infrared picture of the whole sky. The Roman Space Telescope is close to launch. I think it's a year and a half away. And so the Roman Space Telescope is a NASA mission. It also has optical filters, and it is optimized to take wide pictures. And so we'll have lots of deep fields where we can count stars and look for low surface brightness features that way as well. So low surface brightness is where a lot of the future lies, and I just wanted to convey that to you all so that I am now open for questions. And wait, did everything just disappear on me? No. Yes? Stop sharing. Um, okay, I stopped